Everybody, it's video note 7.3 and the Heat Meister is joining us today. Woohoo! So the words that are in red, we're going to talk about those and these 3 bullet points. So these are our objectives. Hey, look, it's Moltato. Moltato, what do you have to say? You're telling me steam burns cause more damage than hot water burns? Let's see. So here's going to be a cooling curve. All right, I'm going to put 100 degrees Celsius and 0 degrees Celsius because I know those are stages for water. So if we're cooling down gas at 100, it's going to turn from a gas into a liquid as it cools down. Then it's going to be a liquid the rest of the way between 100 and 0. And at 0, it's going to freeze, so liquid's going to turn solid, and then you'll have just solid. So why is a steam burn worse than a hot water burn? Well, a steam burn, when the gas hits your skin, it will change temperature to get to 100, and then it will condense. And as it's condensing, this much heat is going into your skin. Ouch, right? So heat, remember, is the energy that causes changes. And so this heat is being lost as the phase changes. Plus, it's at a high temperature, 100 degrees. So, yeah, there's extra heat in during a phase change that's not changing temperature, but it is being let into your skin. Ouch. Thanks, Moltato. All right, so delta H of vaporization is bigger than delta H of fusion. And we saw that this line for the solid to liquid phase change versus this line for the liquid to gas phase change. This one's always going to be bigger because it always takes more energy to overcome forces from liquid to gas. All right, so taking this and turning it to this, you have to overcome all of the forces to get this much potential energy differences. Look how far apart they are. Okay, but from here to here, the molecules are still pretty close, right? These have more rotational kinetic energy, and so they can move around more, but they're still pretty close. All right, hey, look, it's a picture of a mountain and the water and some airplane, well, one airplane. So these represent particles. Those particles, you can't see them, they're there, but those are gases, and gases cause pressure because they hit stuff, right? So there's more gases in the lower atmosphere to hit you, so there's more pressure in the lower atmosphere than there is in the upper atmosphere. You got to think about particles when you think about gas, all right? So boiling point and atmospheric pressure, I'm going to tell you the real truth now. Boiling point, so the temperature when a liquid turns into a gas, depends on the atmosphere, all right? So for a liquid to turn to gas, it has to fight against the particles that are already gas in the atmosphere. So the real definition of boiling is when the vapor pressure from the gas is equal to the pressure of the atmosphere. I have some pictures on the next pages to show you. And then we have a definition of normal boiling point. What's normal? Normal boiling point is the temperature when the vapor pressure from the liquid, so the particles of the liquid that have already turned into a gas, is equal to an atmospheric pressure of 1 atmosphere. So we're defining atmospheric pressure to be 1 atmosphere. And the vapor pressure, when that happens, is going to happen at the normal boiling point. So boiling point is a temperature. Right? Boiling point is a temperature, but it's the temperature when the pressures from a gas that's turning to a liquid that's turning to a gas and the gas pushing down are equal. Here's something for you to memorize. What is pressure? Pressure's the measure of those gas particles in the air. Gas particles hitting stuff. That's pressure. So know all of these values for pressure, and they're all equal to each other. There's different units. Okay, so if you have higher atmospheric pressure, that means more particles in the air, then it's going to take more vapor pressure for the liquid to turn to a gas, so boiling point's going to be higher. And so they have things like pressure cookers that keep liquid liquid, right? A lower atmospheric pressure means it's lower temperatures needed to boil. So here's some pictures, right? Talk about evaporation being from the surface. Right? Those are, yay, you're free, you're free. And when they leave, they take their heat energy with them, and so the rest is cooler. So evaporation is cool. So is boiling, actually, but the temperature doesn't change because there's constant heat being added. Right? Boiling, these molecules that used to be liquid are now gas. Right? And at the same time, all of the gas particles that were in the air, we'll make those red. Look at air, gas particles in the air. They were hitting the surface, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So in order for things to be boiling, the pressure of the gas above the liquid, those are the red ones, has to equal the pressure from the vapor that the liquid forms. And that's when it can boil, and then any molecule can turn into a gas. That's what boiling is. When the air pressure, that was the red ones I did, pushing down on the surface is equal to the pressure of the new gas that's forming. Okay, so why can boiling point change? Well, if you look up here, there's only like 3 air particles. Okay, we'll make 5. As you get lower in the atmosphere, there are more gas particles, so there's more pressure, right? Whoa, look at that. So at sea level, atmospheric pressure is about 1 atmosphere, so the normal boiling point is usually at about 1 atmosphere, which is sea level. Okay, but then less atmospheric pressure at 6,000 feet, so a lower temperature because there's less air pushing down on the surface of the liquid, and so on. So if you want to boil your water at a lower temperature, you only need 79 degrees Celsius at about 20,000 feet. Okay. All right, so can we make a graph of it? You betcha we can. So here's the liquid pentane, the liquid tetrachloromethane, and the liquid water. Okay. This line represents the boiling point. So when the vapor pressure, that's, remember, the pressure coming off from the liquid that has turned into a gas, that's what this is. And this is the temperature. So you can see when the vapor pressure equals 760 milliliters of mercury, 760 milliliters of mercury, that's the pressure unit, equal to 1 atmosphere. So this is normal. And it's going to boil when the vapor pressure equals this 760. That's when it'll boil. So water boils at 100 degrees when atmospheric pressure is 1 atmosphere, which is 760. As you can see, if the atmospheric pressure gets less, and then if the vapor pressure is lower, then and the atmospheric pressure is lower, it can boil at different temperatures. So here we go, right here. If say water's vapor pressure is 400 millimeters of mercury, and atmospheric pressure is also 400 millimeters of mercury, then water can boil at 79 degrees. What? Okay. Now, tetrachloromethane at atmospheric pressure boils at a temperature of 76.5. Pentane boils at 36.1 degrees Celsius in normal atmospheric pressure. Okay. Oh, look, another graph. This time we have propanone, ethanol, water, and ethanoic acid. Right? So, you can see ethanoic acid this is again normal boiling point. So this is the vapor pressure of the liquid, but we're saying, okay, well, when is it going to boil? When the atmosphere equals the pressure from the liquid, that's when it's normal. You can see ethanoic has a higher normal boiling point. So you have to be able to read these kind of graphs and think about them. So let's look at states a little bit differently. Substances can be solids, liquids, or gases. So if you have a certain substance at 150 degrees Celsius and 5 atmospheres of pressure, what state's it going to be? Or what if you have it at 0 degrees Celsius and 0.05 atmospheres of pressure? What state's it going to be? Well, scientists have tested this, they've made observations, and let's see the next slide. You get this, which is called a phase diagram. I'm just going to go back and tell you guys that these are vapor pressure graphs or vapor pressure printouts. Okay, here's another vapor pressure graph. This is a phase diagram. Phase diagram has phases on it. Look, solid, liquid, and gas. So these lines represent phase changes. Okay. Hey, look, there's a phase change between a solid and a gas. So if a solid goes directly to a gas, that's called deposition. Solid goes directly to a gas, that's called sublimation. So there's no liquid, it just goes straight to gas. Okay? But if a gas turns directly into a solid, it's called deposition. All right, what happens along this line? Well, solid turning into a liquid, that's melting. So this represents the melting line. If you're going this way, represents the freezing line. If you're going that way. Okay, so look, pressure on this axis, temperature on this axis. So if the pressure is 1, so here we are at 1 atm, that's normal, all right? And then the temperature is negative 78.5. This substance, which this graph is about, will phase change from a solid directly to a gas at that temperature. Okay. So these are the phase change lines. These are the different states. So you might be asking yourself, what the heck goes on here? This is called the triple point. Triple point. What could happen at the triple point? You could have a solid, a liquid, and a gas existing at the same time. Right? Triple point is when all three states of matter coexist. So at 5.11 atmospheres of pressure, negative 56.4 degrees Celsius, this substance will all be in this container, turning from one to another at all the same time. Okay? All right, what's this? This is called a critical point. Now, you might be saying to yourself, what's critical about it? Well, above this point, you have a supercritical fluid. So it's not really a liquid. It's not really a solid. It's not really a gas. It's something very different. Okay? And look what happens. That's at a very, very, very high pressure, right? And a very, very high temperature. You get a mishmash. Right? We don't really, well, I know scientists have studied it. I've never really seen it. But some cool stuff. Or some hot stuff. High pressure. High pressure, high temp, whatever. Okay. So, look, it's 4 phase diagrams. What are these? These are phase diagrams. All right, and if you're looking at these 4 phase diagrams, there's a lot of information you can find. This one's for H2O. And so you can see at 1 atmosphere of pressure, their liquid and gas can phase change when it's 100 degrees. Okay, so this is the normal boiling point because it's at 1 atmosphere of pressure. All right, if you have lower pressures, right, you're going to have, and low temperatures, you're going to have mostly solid stuff, right? Okay. This one's for carbon dioxide. Carbon dioxide's normal boiling point. And if you notice, this is interesting. It's really a solid turning into a gas. So you've seen dry ice. Oh, look, that's dry ice. Dry ice turns directly into gas without melting at normal atmospheric pressure. Pretty cool. All right, so this phase diagram shows the different phase changes along the line. So you get a triple point and you get a critical point. So make sure you know how to read these and you'll get to have some questions about them. But overall, make sure you know what boiling really means. Okay? None of this old-fashioned definitions. We got to know what boiling really means. It means when the pressure from the atmosphere is equal to the pressure of the liquid that has turned into a gas. That's when it can boil. And then what's normal? Know the conditions of normal boiling point. So that boiling depends on the pressure coming down on it from the atmosphere. Make sure you could read and interpret a vapor pressure versus temperature graph or phase change diagram. All right, this is back from what we've been working on, sketchy heating curve. That's a different kind of diagram than these. This is where you might have a slanted line, or a flat line, or slanted line, or a flat line, or slanted line, or all 5, or just 2, or just 3. You decide based on the temperatures in the problem. Okay. And the key idea of calorimetry is heat loss equals heat gain. That's beautiful. All right, so make sure you've checked out chapters 10 and 14. And after looking through these 3 bullet points, can you define this stuff? Can you read this stuff? Come on, Heat Miser says you can do it. And Molteo's on your side. Peace out. You might wonder what this is about. And so I want you to look at these are high altitude directions. Why would they have that when you're baking a cake? It's about chemistry. So check it out.